I'm very honored and very humbled to be able to present this information for you here today. Now, the source for a lot of this information came from the Arctic News blog spot. That's headed up by Sam Karana and all the amazing Arctic scientists at the Arctic News blog spot. I encourage all of you to visit their website, which I've listed here. You can also like them on Facebook. They are the people who are keeping their eyes on the pulse of what's happening in the Arctic with the methane situation. I'd also like to personally thank Carolyn Baker. She's a great friend of mine and a great mentor, and I've been in her near-term extinction group for about a year and a half or so, and it's a very, very valuable experience for me. I needed to have a place to talk about this information. It's such powerful information, and I reached out and I found Carolyn after reading her book, and in fact she had a group right here in Boulder, so I joined up, and it's been an incredible place to process this very tough information. But the fact of it is Carolyn invites us to inhabit our hearts, not just our heads. The group that we have is called a resiliency group, but we can't grow in resilience only using our minds. And it's important to remember we're not soldiers preparing for battle. We're vulnerable human beings. We're facing a horrific situation, and it's going to be chaos and loss of life. So it's difficult for us to get our minds around this. And my sense is that most of us, including myself, haven't yet grasped what this really means. So an essential part of this process is grief work. This is a shocker, but it's important for you to understand the impact of human emissions. Man-induced global warming is equivalent to 4 Hiroshima atomic bombs detonating every second. This is true fact. And this is something that we really have to understand. Our impact on the planet is immense. I'd like to talk to you a little bit about my own story before we get started and let you understand why it is that I'm so passionate and so committed to this story that we're going to unfold for you today. It takes some courage to understand the story because we have to open ourselves to grief. So the question is, do we have the courage to hold the grief that comes with the end of a story? It's my belief that this is the end of a story. I came to this knowledge about global warming on an emotional level about 2 years ago. I was coming back from England and I was flying to Denver. And it was a direct flight, and our flight for some reason was directed on a more northerly path than it had been planned. And as it turned out, we flew directly over Greenland. Now, I had flown over Greenland several times in the 60s and the 70s as a child because I had grown up overseas. And I knew about Greenland. I knew it was a massive white expanse, unbroken, clean, just this unending sheet of ice. So when I flew over Greenland in early September of 2012, I was not prepared for what I saw. The first thing that I saw were thousands and thousands of icebergs. As we approached the island from England towards, flying west, there were thousands upon thousands upon thousands of icebergs in the water. At first I thought the water was very choppy and very rough, but then I soon realized that these were actually icebergs and they had been discharged from the island itself. I didn't see the island yet. Then we got closer and I saw the island, and it was a towering mass of gray stone mountains rising up sharply. And the ice cover was very, very thin and very dirty and runny, and the whole thing, and keep in mind too, this was the southern half of the island. but it looked like a melted ice cream cone sundae, and it was very, very sad. A lot of very dark, very condensed ice. And I had a visceral awakening at that moment, because the comparison of going over Greenland 30 and 40 years earlier and now was stark, was shocking. And I realized that global warming is very, very much underway. So this is, my effort to tell you about this situation today. So today, we're going to be focusing on methane hydrate. It is a ticking time bomb, and in fact, it does pose a very significant danger to our continued existence on the planet. Let's talk a little bit about methane hydrate as a chemical substance and what it is. First of all, methane hydrate is methane that has a cage of frozen water bound about it on the molecular level. It's trapped in crystals, and it's formed by decomposing organisms and vegetation. And it's actually trapped in the frozen water ice crystals. Chemically, the composition of methane is CH4. That means 4 hydrogen molecules that are bound to a single carbon molecule. Now, those of you who have been keeping track of the hydrogen batteries that have been being built, you know that hydrogen is a very volatile and a very powerful substance, and they've been trying to tap the power of hydrogen for some time as an energy source. So methane is a very volatile substance. This is how it exists. What you see before you is a picture of the edge of the continental shelf in the Arctic Ocean. What you find in the Arctic Ocean is there is initially a continental shelf that goes out some ways, and this is covered with permafrost. At the very top of that continental shelf is a layer of fossil ice that's been frozen for millennia upon millennia upon millennia. We then have a layer of permafrost, which is also frozen. We then have a layer of permafrost and methane hydrate mixed together, also in the frozen state. And under that, you have vast stores of pure methane hydrate, also in the frozen state. This substance of methane hydrate is very, very highly concentrated. It is about 125 times more powerful than carbon dioxide at the molecular level. So, for example, if you have a liter of carbon dioxide, that will equate to 125 liters of warming potential. Methane is much, much more powerful. That's when it first comes out of the earth. It's very volatile. It calms down over time, and it does degrade. So over a 100-year period, methane is really only 20 times stronger with its heating potential than carbon dioxide. But it takes 100 years to get to that degraded potential. So initially, methane is 125 times more powerful, and it's really important to understand this. It's much, much stronger than carbon dioxide. Now, methane hydrate itself is extremely condensed, and 1 liter of methane hydrate is equal to 168 liters of methane gas. So in its frozen form, it's an extremely concentrated substance. As you know, methane hydrate is also flammable. Maybe some of you have seen the videos that have been on YouTube where people poke holes in the ice up in the Arctic and then light a match, and there's a huge plume that just jets out. Actually, energy companies have been trying to mine methane hydrate as an energy source, and they've been somewhat successful in doing so, which, we can all have our opinion about what that means. Now, methane hydrate does pose a danger to life. It's in unstable deposits. What that means is it's frozen. And as the ocean temperatures heat up, the methane hydrate system becomes a lot more unstable, and when it actually melts, it's released directly into the atmosphere as gas. So it goes from the methane hydrate frozen form straight into the gas form into the atmosphere. And this is coming primarily from the seabeds in the Arctic Ocean. We'll talk a little bit about this in just a couple of more slides. But basically, the most important thing to understand about methane hydrate is it has the potential to dramatically alter the Earth's climate. Let's talk a little bit about current methane levels in the atmosphere. This is an atmospheric map of methane, and it goes from 1985 to the current day. And you can see it's got kind of a, it had a little bit of a stop for some reason around 2000 to 2009, but now we're on the upward track again, and our levels of methane continue to grow in the atmosphere. I'd like to point out how we measure methane. Methane is measured in the parts per billion. Therefore, you're not going to smell it. It's not even really existing down where human beings are. It's up where the airplanes fly. And we are currently up around, 1,800 plus parts per billion. So it doesn't take much methane to have a marked effect on temperature rise. What we find ourselves in is a situation here where we are in the devastating final showdown with Mother Nature. This is called the Methane Monster. And the reason we're here is the methane is just starting to come up. Hasn't really come up much yet, but it's starting to as the Arctic gets warmer. It's important to know about how vast the reserves are of methane hydrate in the Arctic. There is an inconceivably huge amount of methane in the Arctic. It actually boggles the imagination. I think there's about 7 times the amount of methane hydrate in the Arctic than all the petroleum products in the world of all the reserves. Now, there is about 100 times, and this is of course an estimate on the Arctic scientist's part, 100 times the amount that's needed to cause a Permian mass extinction event. Let that fact sink in for just a minute. What this means is it only takes displacement of 2% of the methane hydrate reserves that are in the Arctic to cause a Permian style mass extinction event. Now, we all know that the dinosaurs became extinct. We know about the asteroid that hit down in the Mayan Peninsula. But did you know that it was actually the subsequent emissions of methane that rose the temperature so high on Earth and basically did the dinosaurs in? That fact's not much known. What's mostly known is about the asteroid, but the asteroid gave rise to a lot of other chemical processes which gave rise to the release of immense amounts of methane in the atmosphere, and then most life died. So today we find that methane is being released from into the atmosphere in some pretty scary amounts up in the Arctic. And what will happen, and I'll show you why, is temperatures will rise as a direct consequence of these methane emissions, and feedbacks will start to kick in. This is a methane level projection map. It's also a map that shows us of where we've been back as far as 1955. This is a graph that goes through 1955 to the year 2030, and it shows the parts per billion methane that's in the atmosphere. And you can see again how it sort of evened out for a little while, and now we're seeing greater and greater methane emissions. It's my opinion, and the opinion of the Arctic scientists, that we are at the very beginning of the bend of the hockey stick, if you can understand what I'm saying. In other words, as feedbacks start to kick in, the methane levels will increase exponentially. Now, I'd like to talk to you about the relationship between carbon dioxide and methane, because they are very, very highly interlinked. And one, it's like a dance that they're in, and I'll show you how this works. But carbon dioxide directly affects the methane hydrate deposits that are frozen in the ice caps and in the permafrost up in the Arctic Ocean. And carbon dioxide also does jumpstart the methane monster. Let's take a look at the carbon dioxide levels that we see currently in our atmosphere. This is a graph that goes back 400,000 years. It's derived from ice cores. And they are able to measure the carbon dioxide bubbles and date them in their ice core explorations. What they have found is that going back 400,000 years, carbon dioxide goes up, and then it goes down, and then it goes up, and then it goes down. It's almost like breathing. There is a natural cycle of carbon dioxide rise and fall on this Earth. And what we see now is that our current levels of carbon dioxide are off the map. They're right here. This is way out of the normal cycle of what you would see. As you can see, I mean, anyone can see it. So we don't see that these carbon dioxide levels are going to be dropping off. In fact, we're dumping more carbon dioxide into the atmosphere every day, and this level keeps going up. We're currently steadily over 400 parts per million. Carbon dioxide is registered in parts per million. Now, here is a graph that is very, very interesting. We're going to spend a few minutes on it. This is the interrelationship between temperature, carbon dioxide, and methane. There are 3 lines on this graph. Now, we just talked about the carbon dioxide in the previous graph. So the carbon dioxide is this little gray line that goes all the way through here. You can see it. Superimposed over that is the methane emissions levels in the atmosphere. So that is with the black line. So if you can see the methane emissions, it's hard to see because they're very tightly interlinked, and it's almost simultaneous when you look at, 400,000 years ago. But what happens is the carbon dioxide levels go up first, and they jumpstart the methane levels, and then the methane levels come right after that. What happens shortly after the methane starts to come out is that the temperature rises. So you can see that this red line, this red dotted line, is actually the temperature line, and it just is right after, you can see kind of right here, for example, the temperature goes up, and then the and the methane levels go up, and then the temperature rises right after that. So they are very, very interlinked. And right now, we are up here with our methane emissions, and it will not be too far in the future before the temperature follows suit. So let's talk a little bit about greenhouse gas and how they're trapping more heat. Most of our heat goes into the oceans. Now, people are saying, well, global warming can't really, be that powerful because the atmosphere feels exactly the same as it did when I was born, so therefore it hasn't really had much of an effect. You won't be able to feel it with your skin because 97% of the heat that is trapped in our planetary system is digested and melted directly into the oceans. Now, a substantial amount of this heat thus far has gone into the melting of ice, and that's why we're seeing the ice just shrivel away now. This ocean heat is, as the oceans are heating up, ocean heat is transported directly by the Gulf Stream, and it's being transported into the Arctic Ocean. Let's take a few minutes to digest this map. It's very, very interesting. This is a map of where is the heat going. So you can see the first 700 meters of the ocean are receiving the most heat. This again is a map with time being here on the bottom going from 1960 to the present day, and then the heat content going this way. So the higher these things are, the more heat content there is. So what you can see here is at least 70% of the heat that's absorbed by our planetary system is absorbed into the first 700 meters of the ocean. And then you'll see like maybe another 20 or so percent is being absorbed into the deeper ocean now. The deeper ocean is also getting warmer, and that's 700 to 2,000 meters. But then what we also see is this little red part down here. This is us. Right here, we're on land. Only 3% of the heat that's been trapped in our system is going into our atmosphere and our land and the melting of ice. Almost all of it is going into the ocean. And at some point in the not too distant future, the ocean will fight back. This is a sea surface temperature anomaly map, and it might look confusing, but it's actually extremely simple. It's a current map. It's really just this year, but it can show you this is what I'd really like to show you. There are two lines in here. There are red lines and there are blue lines. The red lines are just how the sea surface is behaving in the northern hemisphere. So what you can see by looking at this map, as of the 11th of July of this year, so this is all absolutely current data, the sea surface is 1.5 degrees Celsius, which is a lot more than degrees Fahrenheit, right? 1.5 degrees hotter than it should be. What we find at a global level, however, is that the ocean is only about 1 degree hotter than it should be. So what we can see from this is that global warming is starting up here in the Arctic in the northern hemisphere. I'd like to talk to you about extinctions that have happened on Earth in the past. There have been 5 of them. It's been said by many people that we're in the 6th great extinction, and we'll talk about that in a bit. But let's turn our minds to the past for the moment. The largest extinction we've ever had here on Earth was called the Permian mass extinction. So let's talk about it for a little bit. The Permian mass extinction happened 250 million years ago. This was before the dinosaurs existed. This was before any of that. It was fairly early on in life on Earth. It was known as the Great Dying, and it was the closest we've ever come to extinguishing all complex life on Earth. Pretty much everything died. It says here 90% of the species died out. I just watched another film the other night about the Permian mass extinction, and they said actually 95% of all the species on Earth died out. It was a huge event, and it was a worse toll even than the Cretaceous extinction that wiped out the dinosaurs 65 million years ago. This was the big one. How did it happen? It was caused by global warming. There was extreme global warming when carbon dioxide was released. This is how that carbon dioxide got released. Also, with the Permian mass extinction, there was a large meteor about the size of Manhattan. It skimmed along the Earth near Siberia and opened up, it kind of lanced open the mantle, and a huge rift. I'm not exactly sure how long it was, but it became volcanic, and there were volcanic emissions in this long rift. It was called the Siberian Traps, and it just is exactly what you would think, you know, endless volcanoes emitting carbon dioxide into the atmosphere for a long, long time. Now, there was methane hydrate at this time as well, and there was methane hydrate frozen in our Paleo-Arctic. And as the carbon dioxide began to heat the atmosphere, it jump-started the Methane Monster back in the Permian times. And this caused the methane hydrate to come into the atmosphere. So, when the methane came into the atmosphere, it came out pretty severely. In fact, the entire methane system came out, and the methane plugs at the bottom of the Arctic Ocean broke, and they were actually sealing off a substance called mantle methane, which is formed by a geologic process, and it's formed very, very deep into the Earth at very high degrees. I think 300 kilometers down and at 12,000 degrees. But in any case, it does exist. I've just found out about it this year myself. People are just still finding out about this substance. It doesn't really ever hurt us except when it comes out. It hasn't come out. When all of this happened in the Permian times, the average temperature on Earth rose to about 26 degrees Celsius, and that's about 80 degrees Fahrenheit. That might not sound like much. It was. That's an average temperature. There was a complete and utter deglaciation, and this produced the Permian mass extinction. So, the hard news for us to kind of take on board today is this. If our methane monster is unleashed, and it does appear that it's starting to become unleashed, this will lead to complete deglaciation of all the ice caps and of Greenland and of Antarctica eventually. And it will ultimately, it's such a severe imbalance right now, you know, the way we've pushed it so hard that it will, we think, lead to the extinction of life on Earth. This is a very, very hard fact to take on board. It's impossible to get your conscious mind around it. However, just try and take it on board intellectually and start to work with it. It takes years. I'd like to talk to you about the jet stream at this point. And first of all, let's go ahead and define it. And I'm going to tell you about what's happening with our jet streams here on Earth and what we can expect. So what is our jet stream? The jet stream is a narrow band of westerly flowing air that encircles the globe several miles above the Earth. It's a jet stream, and in fact it is up near where the jet planes fly. It's large. And there are a couple of different jet streams. The one that we're going to be focusing on here today is the Arctic jet stream. That's what we really care about. We care about the polar jet stream. There's a subtropical jet stream, and there's also a polar jet stream in Antarctica, and there's a subtropical jet stream in the southern hemisphere as well. However, for the purposes of this conversation, we're only going to be talking about the polar jet stream today. Now, one of the things that the polar jet stream does to us, for us, as it makes its way around Earth in kind of a ruffle, is it separates the air masses into very distinct places. So we have the polar cell of air mass, then we've got two more cells of air masses that are separated by the subtropical jet stream. The one I'd like to focus on here today is the polar air mass, because this defines our North Pole. So typically this polar jet stream is located about 60 degrees north, and it's generally about 7 to 12 kilometers above sea level. However, the jet streams of Earth are changing. In particular, the Arctic polar jet stream is changing. It's changing a lot. It is slowing down. It is becoming more wavy. It is getting stuck in these wave patterns that are causing extreme weather, and it's not moving on. It is more elongated, it is more stretched, and it is weaker. As it slows down, it loses power, and it's slowing down because the delta, or the difference between the Arctic air temperatures and the air temperatures just below it are weak. They're less, you know, and so it's slowing down and it's weakening, and therefore air that would normally not be exchanged is being exchanged. And what we've seen is that cold air is much more easily moving down from the Arctic. And as we shall see, warm air is moving up into the Arctic. This jet stream deformation is causing extreme weather. Right now, and for a long time now, the jet stream has been stuck in a certain pattern. And it's caused a high pressure zone, for example, off the coast of California. And this is causing all of the air to run north, and the rain that California would normally get, California is not getting. And the reason that California is not getting its rain is directly a result of the jet stream that's currently stuck in this pattern. So here's a picture of our jet stream, and this was taken just a few months ago. This was taken May 15th. And what we can see is that this is not, in fact, a ruffle that's going around the Earth. Usually the jet stream kind of goes around up in this area with a little wave action. But this is not the case here at all. What we can see is hot air pushing, almost like a war, right? Right in here. This is Alaska. This is the United States. We see a pool of cold air over the United States. This is a temperature anomaly map. So this is not actual temperature. This is how far something is out of whack of what the norm is. So what we can see here is that hot air is pushing in from the Pacific, and it's going right through Alaska and pushing into the Arctic. Look at that hot air mass right there. And it pushes into the Arctic, and it is like mixing around. The Arctic and the polar vortex is kind of freaking out, and it's pushing down the Rocky Mountains. The Rocky Mountains are here, and it's pushing down that line into the continent and delivering some very cold weather to the United States. And as I always say, if it's down here, it's not up there. So if you're feeling cold here in the United States and rather strange and inclement weather, please don't think that global warming's all over and that it's all been solved. This is actually the splitting of the polar vortex, and we're going to talk about this in some detail. It's a fascinating subject, and it's happening right now. January 2014. Okay, this is 7 months ago. The polar vortex ripped in half. What? Yes, the polar vortex ripped in half. Let's talk about the polar vortex and what it is before we get into it. The polar vortex is a persistent, large-scale cyclone that circles the poles, and it is located up in the middle and upper troposphere, and it extends into the stratosphere. Pictures speak 1,000 words. There's nothing like a picture to really, really understand what is happening. This is what's happened. In November, our polar vortex still looked pretty normal. It was a 6-sided structure. And you know, 6 is a very powerful number, right? Honeycomb and honeybee hives have 6 sides, and snowflakes have 6 sides. Polar vortexes also have 6 sides. If you look at pictures of Saturn, you can see that polar vortex, and it's a perfect hexagon. The hexagon is the most stable and natural shape in physical existence. So in November of 2013, things were still okay. And you can see 1, 2, 3, 4, 5, 6, our happy polar vortex. Now, in January, things started to go off. There was an invasion and a pushing from the Pacific, from the South Pacific and China. That big air mass pushed right here in Alaska and started to invade the Arctic, and it broke through the polar vortex. Normally that would have been fought off, but our polar vortex is weak. So this is the pathology that we've just talked about. Now when this hot air actually broke into the polar vortex, the center of the cold air split roughly in 2, and the cold air streamed down either side on the continents. And this separated the polar vortex into 2 separate cold centers. This is a map that shows you what has happened a little further on. The first was on January 5th. Now this is January 27th. And you can see here it's pushing hard right in, and it split it. This is the United States. one body, and it came right down the Rocky Mountains, which is right here. That's where it got its initial pull, and it came into the United States. California experienced nothing of this. They're still in drought and hot. Now, this is a temperature anomaly map from March 22nd. So 2 months after the polar vortex split in half, we had an amazing event. The temperature anomalies in the United States went off the charts to the cold area. It also did in Greenland, but who cares? I mean, there's no one up there to experience it. But in fact, one of the little balls of cold from the polar vortex did go to Greenland as well. And Greenland over the winter was colder than it usually is there, which is amazing. But here in the United States, this is where the big news happened. Anybody who lives on the East Coast will remember that it was a horrific winter. And here in Colorado, where I live, it was a horrific winter. It was really, really cold. But it wasn't cold because the Earth is getting colder. It was cold because the polar vortex and that actual air mass that we were breathing came and settled on our heads and brought its cold with it. Meanwhile, in the Arctic, you see something entirely different. Take a look at this bright red here in the Arctic. When this hot air invaded through Alaska from the Pacific and settled into the Arctic, it caused a temperature anomaly that went off the hook. The Arctic has been 20 degrees hotter than normal, and that is Celsius, month over month over month. And that is still the case. That is because the Arctic vortex broke in half. What's going to be the consequence of all of these things that are happening with our poor Arctic? What we're going to see is that the Arctic ice cap is going to completely melt by September of 2015. That's the time when the Arctic ice cap is at its lowest extent. Initially, when it melts, it'll probably be just a month or two in the summer. But then that period of time is going to get larger and larger and larger. And at some point in the future, and I don't know exactly when it will be, but I guess sooner rather than later, there will be no more ice in the Arctic, and that includes the winters. Sea ice is extremely important for our existence here on Earth. I mean, for one thing, sea ice is our Earth's refrigerator, and we're in the process of melting the last vestiges of our refrigerator, at least here in the northern hemisphere. In the southern hemisphere, Antarctica is much bigger. It's going to take a lot longer to melt. But here in the northern hemisphere, we're the ones that are experiencing the global warming. So I'd like to read this to you. This is directly from the Arctic scientists, and I certainly can't say it any better than them. It is scientific language, so I'll read it fairly measured and slowly so you can digest it. Until now, permafrost and the sea ice have acted as a seal, preventing heat from preventing these methane hydrates and causing further destabilization. As long as there is ice, additional energy will go into melting the ice and temperatures will not rise. The ice acts as a glue, keeping the soil together and preventing hydrate destabilization from pressure changes and shock waves resulting from seismic activity, that's earthquakes. Once the ice is gone, sediments become prone to destabilization, and heat can more easily move down along the fractures in the sediments, reaching the hydrates that had, until then, remained stable. This is going to cause some intense weather. Actually, the intense weather is already starting, but it's actually going to get worse. Everybody remembers when talking about the weather used to be considered small talk, you know, how's the weather? No big deal. Now I turn to the Weather Channel all the time and all sorts of international weather stations to kind of clock what's going on, because it's really unfolding. The hurricanes are bigger, the tornadoes are more powerful, more wide, Just a couple of weeks ago here in Colorado, 2 people on 2 separate days were killed by lightning in Estes Park, and it was a really unusual event, and we've had tremendous lightning here. So everything is getting bigger, tsunamis, everything. So we can expect that we will have extreme weather coming our way. This is because we have higher levels of all of these greenhouse gases that we've been talking about, and this is trapping a lot more heat in our planetary system. And this is resulting in more heat waves and other sorts of weathers. Stronger winds and greater evaporation is leading to stronger rainfall. Maybe you have heard in some places you get a year's worth of rainfall in just a few days now when these things hit. So global warming is contributing absolutely 100% to extreme weather around the globe, and you cannot look at a certain storm and say, well, was this storm caused by global warming or was this storm not caused by global warming? The whole system is connected, and you can't pick it apart like that. It doesn't work. So global warming is affecting us strongly in the weather events. In fact, weather events are going to get stronger by about 10 to 20 times, if you can believe that. Now, that is very, very, very hard for us to get our head around. So as we said before, right now the jet streams are becoming slower and wavier and more fractured, and it's leading to weird behavior, including California's drought and including an event that I personally went through here in Boulder, Colorado, and it was the flood of September 2013. It hasn't even been a year. But I'd like to tell you how it happened because it was not in the news, and this is actually the pathology of how this flood happened. Those of you who are not familiar with the Colorado flood of 2013, very briefly, in 8 days we received 18 inches of rain. That's 18 solid inches of precipitation in 8 days. Here in Colorado, we live in a semi-arid existence, and we receive about 18 inches of rain a year. So we received an entire year's worth of rain in 8 days. And I lived through it. I watched the rain come down for 8 days. I was amazed. And I immediately went to NOAA, which is a scientific site about the weather, where you can find out what's going on any place in the world. And what I found was this. There were 3 extremely powerful hurricanes that were happening at that very moment in Mexico. There was one on the Pacific side, and there were 2 over on the Caribbean Gulf side, one a little bit up from the other. So these 3 extremely powerful hurricanes that caused tremendous damage in Mexico, some of you may recall, it whipped a tremendous amount of energy into the troposphere, way above where we would usually look for weather. And in fact, our weather people here in Colorado did not see this on the horizon. They thought we might get a shower. They didn't see it because they weren't looking in the right place. The weather that hit us came sort of like in a wormhole up from Mexico in a phenomenon called an atmospheric river. And during the 8 days when this atmospheric river came directly onto our heads, it delivered the amount of water that usually runs in the Amazon River. It was a phenomenal event, and it has changed the way Boulder looks. Actually, I've never seen Boulder look so verdant and green. It has completely changed the vegetation in this area. We're going to talk a little bit about methane hydrate deposits in the world. So, we've been talking about the methane hydrate deposits in the Arctic Ocean, and also those go into Siberia and the Canadian permafrost. But did you know that there are methane hydrates in New Zealand and Antarctica in huge quantities? This is a new discovery, and I'm going to share it with you now. So, New Zealand. We don't usually think of New Zealand and methane hydrates in the same breath, but in fact, there are stores of methane hydrates that have been found in New Zealand that are absolutely phenomenal. This was discovered this year, in fact, May, just a couple of months ago, and it was discovered by a joint New Zealand and German research team, and they found a huge network of frozen methane hydrate located off New Zealand's east coast, and it's huge. The way they discovered it is they saw all these methane flares coming up from the seabed, and they went out to investigate. And in a 50 square kilometers, they found 99 gas flares that they counted at that time. And these were venting from the seabed off the east coast of New Zealand. And they were columns of methane gas about 250 meters high. Now, interestingly enough, they discovered a brand new thing that I had never heard of, and that is a methane hydrate landslide area. So these are the equivalent of glaciers, but it's with frozen methane instead. And they're about 15 kilometers long, and there are a lot of them, and there are these kind of moving methane hydrate landslides that exist off the coast of New Zealand. Let's take a look at this. So in a 20,000 square mile area, which is huge, right? It's this whole area, they have found huge reserves of methane hydrate. In addition, they found a huge giant pockmark. This is the result and kind of an artifact from the past. A huge methane eruption happened sometime in the past in New Zealand, and they don't know when it happened, but it's a giant crater, sort of like a volcano crater, but it's left over from a methane eruption. They also found other methane eruption pockmarks over in this other area. So New Zealand is now on the methane map. So with that, let's turn our minds to Antarctica. What they have seen now is that methane emissions are currently happening in Antarctica. In April of 2013, they found, for the first time in my knowledge, high methane readings over Antarctica. It's in this red area in eastern Antarctica, which you wouldn't expect. We always hear about the west because the western part is the part that's melting uncontrollably at this point. But everybody thinks the east is stable until now. There are huge methane readings that are coming over the Arctic heights in East Antarctica. So look at this. As we've seen in the Arctic, this led to a temperature anomaly that was directly resultant from the methane emissions. Please take a look at this map of Antarctica at the bottom. What you'll see here is a huge temperature anomaly, and this part right here that's red is the part that we just looked at on the map, but it's stretched out. And then again, in September of 2013, huge methane readings were seen again. So it seems to go possibly in a 6-month cycle, but they're still learning about it. But Antarctica is now also a source of methane. However, not as much as the Arctic, it must be said. So you might be curious, what caused these huge methane releases in the Antarctic? Well, it's very, very interesting. So let's take a look at this map. This graph here shows us that the temperature, this is time on the bottom, and this is the anomaly in temperature, all right? So as we go along in 2000, this is a map from 2000 to 2014, things are fine. We're having ups and downs in Antarctica. This is the anomaly off of the normal temperature, nothing too off of the average, right? Then we had a 3-degree drop in 2013, just a 3-degree centigrade drop, and then it popped back up, which is what it usually does after a drop. It pops back up. But then, instead of kind of settling down again, it went off. and it hasn't been back since. So it was taken off by the very volatile nature of methane. Now the Arctic. Let's go back to the Arctic and talk about it, because this is really where the rubber meets the road. The Arctic is the front row seat for rising temperatures. I'll tell you what's happening there. Currently, water temperature is on the rise in the Arctic. And also, the temperature of the water that's near the bottom of the ocean is also rising. You'll remember that on the continental shelf, there extends a whole layer of fossil sea ice that's at the bottom of the ocean that covers the methane hydrate. This is starting to melt, and heat is starting to penetrate the sediments that are at the bottom of this continental shelf. This is causing methane hydrate destabilization, and we're starting to see large methane releases. This is causing the Arctic to be very hot, and it is still much hotter than normal, 20 degrees Celsius hotter than normal, to be honest, and it has not come back down. There are a number of feedback loops. Feedback loops are all accelerating warming in the Arctic. Right now, a lot of the energy is going into the melting of the ice. But once that ice melts, the water is going to heat up much more quickly, and this is going to cause temperatures in the Arctic to rise further. Methane releases from the sea floor, and the Arctic is warming up even further, and this is triggering more methane releases. So one methane release will cause warming. This will trigger another methane release, and this is where we enter a spiral of runaway global warming. There's no easy way to say this, but it is something we must start to take on board and start to process as souls and beings. This is going to cause starvation, destruction, and ultimately, in my opinion, probably extinction. We don't know the time frame. So let's talk a little bit about ice loss, because it's all starting here. Ice loss means more sunlight gets absorbed into the sea instead of being reflected back into space. And this is one of the feedbacks that's accelerating warming in the Arctic. We all know from practical experience, if we put on an all-black outfit and go outside on a nice, bright, sunny day, we're a lot more likely to get warm than if we wear a nice, breezy, cool, white outfit, because when you wear white, the energy is actually reflected by the white color off of your outfit, and you don't get nearly as warm. So let's talk about some of this feedback action that we're seeing. It all starts right down here in the lower left-hand corner. This is emissions. Emissions are us. So we're dumping a tremendous amount of carbon dioxide into the atmosphere, and it's growing, as you know. And this is resulting in the initial global warming that we're seeing. But it's also releasing a lot of soot. It's a dirty sort of energy that we have. It's a terrible energy. And this is causing albedo changes. Albedo is the reflectivity of ice. And I saw with my own eyes when I went over Greenland, the amount of soot that has condensed onto that ice cap is unbelievable, and it has darkened the ice cap incredibly. And that is also causing the ice cap to melt much, much more quickly in Greenland. So as snow and ice begins to melt, things get warmer, and then the Arctic methane stores start to weaken. That's where we are right now. We're in this box. If you ever want to put us in a box, we're here and we're here. The methane has not yet released in earnest. But as the Arctic methane stores begin to weaken, they will begin to release. And as they release more systematically, we enter global warming, runaway global warming. I'd like to take a few minutes to talk about a phenomenon that's now happening on Earth. It's called the methane veil. The methane veil currently envelops the entire northern hemisphere, and it's thickening in our atmosphere. It's not in the south yet, but it does envelop the entire United States. It's progressing at about 1 kilometer a day. Some important things to know about this methane veil. You won't smell it. It won't choke you. It's in the parts per billion. And it's up where the jet planes fly, so it is invisible to us as organic beings here on the Earth. So we do have a global warming veil that's currently enveloping us, and this is because we're experiencing huge methane emissions. In fact, we had a real kind of like a sequence of methane emissions between September 2013 and March of 2014. So that's the Arctic winter. So over the last winter in the Arctic, methane emissions began to actually take off. And that was not what I would have expected. I thought it would have happened in the summer, but in fact it happened in the winter. While these methane emissions have taken off, they've moved up in the atmosphere, the concentrations, and the veil has moved closer to the equator. I'd like to spend a few minutes on this graph. It's very interesting. This is methane atmospheric concentrations, and this compares 2 time periods of the same time period. 2013 is above, 2014 is below. The red bar on the bottom is the atmosphere that's nearest the Earth. The blue bar on the top is the stratosphere, and that's the atmosphere that's furthest away from Earth. Anybody can see, looking at this, that the layers in the atmosphere are starting to saturate more with methane. It's very, very easy to see, and this will increase as time goes on. To reiterate one more time, 97% of the trapped heat in this planetary system is being absorbed directly by our oceans. And this is causing sea surface temperature anomalies, and they're currently very high. I'd like to spend a few minutes on this map. This is a fascinating map, absolutely fascinating. This is a temperature anomaly map from this month, July 4th, 2014. What we see here is that things are hot. However, what you also see, here's Greenland. We all know what Greenland looks like. There's not like any hotness up here. Why is that? That's because this is still ice. This is how the ice looked, in fact, when this picture was taken. So we don't see any sea surface temperature anomalies where there's ice. However, where there's not ice, you do see it. So please take a look just to the east of Greenland, right here in this dark red area. This is where there's a fault line that runs all through here, and it terminates up through here. So what we see is that the sea surface temperature anomalies are really very, very high. They're like 4 degrees hotter than normal, 2 degrees hotter than normal. That may not seem like a lot, but it's a huge amount. Please keep in mind this is centigrade. But, you know, the other thing that we're also seeing is there's some blue on the map. And why would there be any blue on the map? Why would you have cold sea surface temperature anomalies in this situation? Well, I'll tell you why. There are glaciers that are melting, and they're dumping vast amounts of rain into the ocean. Vast amounts of melted ice into the ocean. And wherever that ice and that cold water is being dumped into the ocean, you are having temporary pockets of cold anomalies. So you'll see here off the coast of Alaska, right? This is where the Columbia Glacier is, and this is being dumped out into the sea. That is disgorging an enormous amount of water into the sea right now. Also, please look at the southern tip of Greenland right here. Greenland is experiencing a great amount of melting right now, and what we see is that this cold water is affecting the entire area around here. As you can see, a lot of the water is being dumped right here, and it's causing these pockets. The same as in Scandinavia. Anywhere we have melting glaciers, we have temporary pockets of cold water. Now, as we said, global warming has heated up the ocean currents. And these ocean currents are affecting the Arctic, and it's helping to destabilize the methane hydrate. And what we see are increasing volumes of methane being dumped into the atmosphere. I'd like to show you this. This is a fascinating map. This is a map of our ocean's currents. And if you can just follow me a little bit, what we have is this. Follow this warm cycle and how it goes. The cold air eventually surfaces right here where Alaska is. Consequently, that's also where the hot air is pushing into the Arctic, but it surfaces here. And then this hot current is on the surface of the ocean, and it goes all through the Pacific, picks up a lot of heat here in the Philippines, in Indonesia. It goes under South Africa, and then it makes a swing right through the Caribbean. And what happens right here? Well, it makes a U-turn, and it gets cold. Well, obviously, if it gets cold, it's delivering its heat. So it delivers all of its heat right here, and that heat goes directly into our Arctic Ocean, and it melts our Arctic ice cap. I'd like to talk to you a little bit about permafrost. Permafrost are the vulnerable carbon pools that are in Siberia and also in Canada. And what we have found is that the permafrost is changing a lot right now. Some of you may be aware that recently in Siberia there was a really large hole that opened up in the earth where the permafrost was, and it just sort of like dissolved, and it's this massive crater, and it keeps getting bigger. So permafrost is not stable. And we can expect more of the permafrost to rise. More of the permafrost to melt, and this will cause temperatures to rise when the methane in the Arctic comes out and the permafrost allows the methane to come out. We are expecting at this point a rise by another 10 degrees Celsius within decades. This is not my number. I haven't made up any of this information. This is from the Arctic scientists. Let's take a look at the permafrost stores we have around the world right now. This is Siberia here. You can see that there's all this permafrost right here and all through Scandinavia. There's also permafrost all through Canada. There are vast permafrost reserves, and they're in the frozen state right now, but they won't be frozen once it gets hotter. Now, there's a phenomenon going on in the Arctic right now. You might not have heard of it, but it's starting to really pick up, and it's earthquakes. There's a fault line, as I said, that goes right through the Arctic, and it starts right along Greenland, it crosses the Arctic Ocean, and then it extends into the Laptev Sea and over into Siberia. So two continental plates come together right in the middle of the Arctic, and it's usually very quiet up there. However, as the Arctic ice has been getting less and less and the Arctic Ocean has been getting warmer, this area has lately been hit by many large earthquakes. And what has been seen is that this is causing destabilization of methane hydrate, and it's causing it to come up now. Let's take a look at this fault, because this is really where it's happening. All right, so this is a map that might be a little bit difficult for some of you to understand, but the United States is in the upper left-hand corner. We have Greenland just to the left, and then we have the fault line. These are some of these little Arctic islands, Svalbard and so forth. But look at this fault line. It goes right through the Arctic, right here. This is called the Gokal Ridge, and then it goes here. Here's the Laptev Sea on the other side of the Arctic, and this is showing some earthquakes that hit the Laptev Sea during this time frame. These were some earthquakes that happened in this June, a couple of months ago. But it's really interesting to me, kind of the chronology of the earthquakes. And I went back and I kind of did a deep dive into these earthquakes to try and understand what's happening. And this is what I think. There was an absolutely huge earthquake. It was 8.3. It hit, just a little over a year ago, May 2013. And it was very, very deep. An 8.3 earthquake hitting at 378 miles deep. This is a deep earthquake. What this means is that the continental plate was affected. Deep earthquakes affect Earth at the continental plate level. And this was a big one, and it was deep. So it jolted the continental plate. Then what we saw very shortly after, within days really, for about 5 days, there were peak levels of methane right where that earthquake happened. And so a huge amount of methane came up from that earthquake. Now, what we've seen lately is in Greenland, there's a huge amount of earthquakes taking place. And this is because of a phenomenon called isostatic rebound. You might not have heard of isostatic rebound. What is it? It's this. Greenland itself, as a landmass, is starting to get lighter. Why is it getting lighter? It's getting lighter because a tremendous amount of water is being disgorged as the water is melting. And that is causing the actual Greenland island to rebound and actually get lighter. And so it's kind of starting to lift up ever so slightly. And this is causing a number of earthquakes along the east coast of Greenland. There's a phenomenon called earthquake triggers. Anybody who lives around earthquakes probably knows this. But one earthquake can trigger a lot of other earthquakes, often called aftershocks or other names. Some of the aftershocks can be just as big as the initial earthquake. Now this is an interesting map. Take a look at this. This is a map of all the earthquakes that have happened in Greenland the first 6 months of 2014. Sorry, this year, 2014. There were over 20 earthquakes that took place along this fault line that is being activated currently by the isostatic rebound nature of Greenland. And take a look. It's just, here's clusters of them, and then all along. But they're going further up than this. So we're going to start to talk about where are these earthquakes occurring in the Arctic. So this is a sequence of earthquakes that I'm going to take you through rather quickly. The first earthquake occurred here in our sequence that we're looking at here today, March 6th, 2014. An earthquake just north of Greenland, but in the Gakal Ridge occurred. That was a 4.5. Large methane releases occurred after this earthquake hit. 6 weeks later, April 13th, 2014, a little further up the fault, another earthquake occurred, and that was at a magnitude of 4.5 on the Richter scale. About a week later, another earthquake occurred on the Gakal Ridge a little further down, and that was April 22nd. So you can see it's going boom, boom, boom. It almost feels a little bit like a zipper on the Gakal Ridge. And then we had a big one. We had a 5.1 in Greenland, C, April 26th, and this was right near Svalbard Island, which has recently been the source of a lot of methane emissions and a lot of extra heat in Svalbard. Now, anyone who looks at this can see the Laptev Sea is going off the hook. This is in parts per million in volume, and this is basically methane emissions in the Arctic Ocean by latitude. So the way this particular graph works, the more left you go, the further up you are on the Arctic. So, you know, that would be the North Pole at 180, and the further to the right you go, the further on down you go down the globe. But what you can notice is right here in the Laptev Sea, it is off the hook. This should send alarm bells ringing through everybody's consciousness. We can see something is clearly not right. I'd like to talk a little bit about another substance. It's not methane hydrate. It's mantle methane. We talked about it just a little bit earlier. It's produced at very deep, about 300 kilometers down, between 100 and 300 kilometers down. It's produced by a geologic process. Mantle methane is not a biologic process. It is, in fact, a geologic process. It's produced at very high temperatures, 1200 degrees centigrade. It's produced in the mantle. It's basically a geopressured reserve of mantle methane. It exists deeper in the mantle, but a few places in the Earth it's kind of come up closer to the Earth. And one of the places where it's a little bit closer to the Earth is in the Arctic. Fortunately for us, this whole system is being sealed right now by methane hydrate, and it's got a ton of methane hydrate on top of it. However, the problem is if this methane hydrate seal goes away, we will have massive methane emissions that will include mantle methane, which is fairly incomprehensible. If this does happen, there is no way to reseal this system. The Earth is going to do whatever it's going to do, and nothing we do, no geoengineering effort on the part of humans will have any effect whatsoever. I'd like to talk to you now about the extreme Arctic methane eruption zone. This is really, we've spent this whole talk to get to this point. So please take a look at this map. Again, this is the Arctic Ocean. Yeah, you see Greenland here, and then you see here's the rift. This is the Gokul Ridge that we've been talking about. And then at the end of the Gokul Ridge, we have the Laptev Sea, and we have Siberia. But before we get to the Laptev Sea, look at this little red dot here. This is the extreme methane eruption zone, and this is where most of the methane is coming up right now, that area. This is a methane eruption projection map. It looks scary, I admit. It is, in fact. It also shows the volatile nature of methane. Methane doesn't come up so steadily. When it comes up in flares, I mean, it will come up in these huge emissions, and then it'll settle down for a while, you know, and then it will be gone, and people will think, oh, well, that's done now. And then it'll come up again and again and again, and it has a feedback system. At a certain point, it will just erupt, and we do not know when that point's going to be. So what we see is in the extreme methane emission zone, there is a much deeper source of methane, and that is the mantle methane, and that's coming up right near the Laptev Sea. Here is a map. If you've ever wondered how is the methane hydrate mapped out in the Arctic Ocean, this is how it's mapped out. You might want to refer to it. I thought it was interesting just to know where the methane stores are. Now see this again, I'm going to point this out again. This little blue spot, this is the extreme methane eruption zone. So it's very interrelated. All right, so this is what we think is going to happen. It's a hard truth, but we do have to go through it. The Arctic ice cap will melt most probably, as far as they can tell, towards the end of 2015. At that time, the Arctic Sea will be aggressively heated by the sun because, as you know, during the summertime, the Earth points much more directly. You know, the North Pole points directly at the sun, like 23 hours a day or something like that. And then at that point, the Arctic Sea is going to heat up. And the Arctic cold air will be confined mostly to the Greenland ice cap and nowhere else, because it won't be confined to the Arctic Ocean anymore. There are going to be methane emissions at that time, and hot air will flow south towards to the United States. This will cause a feedback loop. This will further heat up the Gulf Stream, and they expect that an anti-clockwise circulation will start up around Greenland, where the remaining cold air will exist in the northern hemisphere. Again, I can't stress it enough. Sea ice is very, very, very important to our health as a planet. I'll say it one more time. Ice loss means more sunlight gets absorbed into the sea, and this accelerates warming in the Arctic. So, sea ice extent, let's talk about that. Sea ice extent means how far does the ice extend at any given time. In April of 2014, that's usually the sea ice extent maximum. In April of 2014, our maximum was the second lowest on record. March of the previous month was also the second lowest on record. Now, this is resulting in the demise of the Arctic ice cap, and we're depicting it here with the Arctic death spiral. This is a very, very interesting graph that goes from 1979 to the present day, 1979 being straight up as a clock, and you just follow it around. Month by month, you can plot how the ice has done on any given month over time. Now, the month I'd really like to pull your attention to is September. September is black, as you see. In 1979, it was up here around 17. It was pretty even, up and down, up and down, up and down, and then it looks like around 1992 or so, things started to change very, very quickly. And look now how quickly things are changing. We will shortly be at the 0 mark. In addition to the Arctic sea ice extent shrinking, the thickness of the Arctic ice is also going away. I mean, the Arctic ice is extremely thin, it's extremely fractured, and there is no more multi-year ice in the Arctic. It cycles out, and we have sort of a thin covering. Polar scientists are not able to go where they used to go in the Arctic anymore because the ice is too thin. This is another way to look at the Arctic sea ice extent. This is another map that shows us through time what's happened to us. This dotted line that you see here is 2012. So this represents a year. So here we have from January to December. How did our ice do from January to December? Well, you can see that it goes up, and then here in April we're at the maximum, and then it goes down and we reach our minimum in September. This minimum was reached in September of 2012. Now I'd like to show you something else. It's very, very interesting. Look at this right here. September of 2012 is a dotted line. This little gray line right here, this is us today. We are just about to cross over that record minimum of ice right now, and I'm quite sure that when 2014 is all done and recorded, that we will have the lowest ice extent on record in Earth thus far. So, net, The outlook for the Arctic sea ice remains extremely bleak. And as we said before, this is going to cause more sunlight to get absorbed into the sea. This is going to cause further methane to be released. And we are going to see much stronger storms, much stronger heat waves, much stronger tornadoes, much stronger tsunamis. Everything is going to get stronger, and it says an increased risk of total ice collapse. I would actually say a guarantee of total ice collapse either at the end of 2015 or 2016. Here's another way to look at it. This is the sea ice volumes for extents for September over time from the year 1980 to the present day. And that's when we started keeping records of the sea ice. That's why it goes back only to 1980. But what we see is that in September, which is the lowest, the month for the lowest sea ice extent, you know, it goes along, and then suddenly it begins to drop. It looks like we had a little recovery here, but believe me, that's not enough to get us out of this. We will shortly be to zero. Unfortunately, when this happens, this is going to unleash a interlocked feedback loop that is going to ensure our doom. And I am an absolute proponent of near-term human extinction. I wish I didn't believe that. I don't want to believe that. I'm not a conspiracy theorist. I'm a very stable person, but I've looked hard at the data, and this is what I see. And I see that our time on this earth is coming to an end, and I did not know that this was going to happen to us, but we've all incarnated here at this time, and I think this is our challenge to integrate this body of knowledge. We are facing near-term extinction as a species. We are a planet infected by humans. And, you know, I mean, it's good to remember we're eternal beings. We've existed for a very, very long time. We'll exist into the future. But I do not think that we will exist here on Earth as organic beings. I'm not sure that it will be fit for life. This is a temperature map of what they think is going to happen. The line to pay attention to here is this white one. We are at the slippery point of the hockey stick. You know, people are being quite cocky and they're saying, oh, well, global warming is over. Oh, well, it's all said and done. You know, it's not going to happen. It's on a plateau. It's sad that we can't deal with it. It's so sad that we have to deny it rather than looking it in the eye and trying to do something about this situation. But what we have shown as our maturity as a species is that we would prefer, for the most part, globally, I'm not talking at the individual level, I'm talking really at the mass consciousness level, we would prefer to stuff this one under the carpet and not deal with it and let the storms get bad and then say, oh my God, I guess it was real. We are here. This is what they call the hockey stick. We're about to enter it. I don't know how fast it will progress. This is all projection. So, this has been a sobering talk here today. It has been a difficult thing to give, but I thought it was a very, very important thing for everybody to understand. We are currently engaged in the great anthropocentric extinction. This is the 6th extinction of life on Earth. The pace of climate change continues to accelerate, and it now appears inevitable that the great anthropocentric extinction currently unfolding will include the end of life as we know it. No easy way to deliver that message, so I thought we'd just hit it head on that one. So, I'd like to read you this from Chris Hedges. He says it so well. A society that loses the capacity for the sacred, that lacks the power of human imagination, that cannot practice empathy, ultimately ensures its own destruction. So, in conclusion, I'd really like to thank you for your attention here today. I'm humbled and honored to be able to get this information to you, and I think it's so important that we begin to process it together.